So we were talking last time about the Poisson distribution, and we had some nice examples. We had folks on telephone poles. We were talking about originally just kind of a single sample scenario to motivate why we might use the Poisson distribution to make inference about counts and rates. And I'm going to navigate faster this way. We talked about the Poisson regression model, which we said was really a model can be written as either the model of a rate, which is written here here's the rate form on this line here, and in the box is the log of the rate form of the Poisson regression model. And then we also showed a version here, which is kind of the better way to think about it from a computational point of view, and it's the log of the expected value of the count is a very similar model. It's the same linear function, but now we have the log of the offset. This is on slide 18 for folks. I'm just jumping around from what we did last time. And so this version that's the log of the counts version is what SAS uses, and you have to specify this thing called the offset. And so one of the contexts in which we use Poisson regression is really to look at data like this, like the skin cancer example, where we don't really have individual responses that we're modeling anymore. The Poisson distribution, as we talked about at the beginning, is good for it's an alternative to the binomial distribution for talking about binary outcomes, but what it does is it describes the count of binary outcomes. And one of those situations where you're describing the counts of binary outcomes is something like this, where you have surveillance data and we don't actually have individual level data. You can't, so this is not as amenable to our logistic regression 0-1 kind of thinking, and we don't even have individual covariates. And so here we said that the Poisson distribution might be a really good way of describing these data and answering questions like this. Is there a difference between cities? Well, what happened? Is there a difference between cities after we control for age confounding, when the age distributions are different? How do we think about effect modification? Can we model effect modification, right? So here we had that across the age spectrum, the rate ratio is changing between the city versus city rate ratio is changing, and you may want to say, geez, is there effect modification? And so the Poisson regression model offers a way for doing this. And we said the data looks something like this, where the key data elements are the outcome the outcome variable is a count of the events. So here this is the number of skin cancer cases. There's some covariates that's kind of in the middle, and on the right side is the person time. And we said you have to take the log of the person time in order to have an appropriate model for inference. It's not really a variable in the model in kind of in the classical sense. It's this extra nuisance thing that the model needs to take into account, the offset. It doesn't have a beta term associated with it. It's just this count thing that you got to put in the model that the model is going to deal with. And we said that there's two ways to write the model, for the skin cancer example, there was two ways to write the model. That is, one that defined the dummy variables explicitly and one that didn't. But the basic idea in GENMOD was that you have a typical looking kind of model statement, and that to specify that you want Poisson regression from any other old regression that's out there, you need to specify that the link is the log and distribution equals Poisson. And again, this tells it the function that it's got to do under the hood to linearize the equation. And then this is telling it that the distribution of the residuals is Poisson rather than binomial or normal or other distributions that we use in other regression forms. And then you got to tell it the offset, which again is this log of person time or whatever the denominator or quantity is, and you got to make that manually in a data step. So it's not gonna do it for you automatically. And so when we fit, this is where we left off, is okay, what happens when you fit this? You get output that's rather kind of typical looking at the beginning here of any of the statistical modeling procedures. SAS tells you I have 16 observations, which we know. It's telling us here that there was a class statement with age group. It had 8 levels to it. We're going to talk about how to use some of these goodness of fit criteria here. We're going to use the Deviance statistic to talk about statistical testing soon. That's going to be the next slide set. So I'm just going to jump to the next piece, which is you get a table of very typical looking kind of estimates for all your terms in your model, your alpha and your betas and your gammas, whatever you want to call them. Here's all the pieces in our model. We had the estimate for the intercept, city, and all of the age group dummy variables are represented here as well. You have the standard error, confidence intervals, all that kind of stuff. We have this thing called the scale parameter. We'll talk a little bit about that. Right now, you'll see what's important is that the scale parameter is set to 1. Okay, we'll get back to that. If you don't do anything, if you don't ask GENMOD to do anything special, this is going to always say this line is going to always be the same. It's going to say 1 with 0, and we'll talk about that. This is not really a term in the model. This is just an FYI thing it's telling you at the bottom. And notice this is the referent group. So GENMOD is, so interestingly, GENMOD puts the referent group in here with a whole bunch of zeros. I don't know why. It just does. So in logistic, if you said class, age group, I think it would just show you 7 dummy variables and not this piece on the bottom. So again, there's 8 levels of age group, so we really only expect 7 dummy variables, and nothing is ever consistent in SAS. So yeah, so you have that extra line here. So the question is, well, where's the rate ratio, right? I want the rate ratio, right? And we said that the rate ratio is e to the beta, or possibly could get more complicated if we have effect modification. So natively, GENMOD is not going to give you a table of odds ratios like in the way that logistic actually can actually just give you, has an odds ratio statement, it has a table of odds ratios, and it just gives you things automatically. You have to always ask for what you want out of GENMOD with the estimate statement. So it's never going to automatically give you e to the beta or have special statements. And the reason is that GENMOD is really it's for a whole family of generalized linear models. It can do 40 different types of regression models, and it doesn't have special nice things for Poisson regression out of the gate. So you're going to have, if you want a rate ratio, you're going to have to use an estimate statement to do that. So for example, if you just want e to the beta, which in this no interaction model was the Dallas versus Minneapolis effect, the increased rate of cancer in one city versus the other, you have to explicitly ask for it with an estimate statement. And it looks very similar to the other statements that the other estimate statements and the other procedures. So it's going to be estimate, whatever you want to call it, in the quotes. That's the label. And then you go city 1 for, that there's a 1 next to the beta for city and then zeros everywhere else. So you go city 1 /exp for exponentiate it, please. So what you get is output that looks like this. And this is, by the way, also different from how logistics output looks. If you did a similar type of thing in logistic, it's going to give you the exponentiated answer only, but for some reason GENMOD gives you the answer on the, what scale is this first one? Log. It's a log model, natural log. It's on the natural log scale. This is the untransformed original answer on the log scale. And here we get the exponentiated answer over here. Though actually this is weird. This is repeating down over here. Weird. It's actually giving us the answer twice. This is the log answer over here that I was looking at, but I didn't realize that GENMOD can also give it to you over here. So it's giving the answer twice. I didn't make SAS. I don't know. This is the log answer. This is the crude answer. This is the exponentiated result. And then I guess it's repeated again over here. This is the 95% confidence interval around the rate ratio estimate of e to the beta. So 2.2 is the estimated rate ratio. Controlling for confounding by age. So we have all these V terms in here for the age group. This is an adjusted effect of the cities controlling for age. 2.2 is the adjusted rate ratio. And here's the confidence interval twice. And then here is a chi-square test actually for whether this is equal to 0, whether the rate ratio is equal to 1 or not. So this is actually a chi-square test that it's giving you as well. So this is the basic machinery of GENMOD. We got to put these pieces on the model statement as options to tell it that we're requesting a Poisson model and not as something else. And then to make rate ratios, we need to always be using the estimate statement. Any questions before we go to the next one? Okay, inhale, exhale, more Poisson regression. Same guy. He's kind of smirking about something. I think he knows he's really smart and we're not. And he's actually known to be one of the most prolific scientists ever. He wrote something like just hundreds of books and these large treatises on the, on the orbiting of the heavenly spheres, with those kind of, and just like huge books on physics and mathematics. And I think he's the most voluminous guy ever, and he knows he's better than us. So this is just okay. So we're going to start off by talking. We're going to take a little step back and talk a little bit out under the hood what the Poisson model is doing, and I'm going to show a few other data scenarios to get you really thinking about how versatile this versatile and potentially confusing all the different ways you could apply Poisson regression get pretty interesting, and then we'll talk about a few specifics around hypothesis testing in the Poisson regression model. So, okay, so the Poisson distribution assumption, which we're going to talk a little bit about, again, just what is going on under the hood here. So what we're saying here when we model something with Poisson regression is that we have a certain model. We're observing Yij's, these counts. In the ith count for the jth subgroup, we have some person time associated with each of those observations of data. This little L sub ij. And we're modeling the expected value of the counts in a given group. Right? We observe in that age group in Minneapolis a certain count. And that was one observation on that subgroup, but we actually are trying to understand on average what's going on in all of these groups. That's why we're modeling the expected value of y. And what we're assuming here is that the counts are sampled from a Poisson distribution that on average has a mu parameter, a mean parameter, this key piece of the Poisson distribution. And on average, that mean parameter this is the expected value of the counts, and it is also equal to the rate times the person time. Like if I knew exactly what the rate is in 13-year-olds in Minneapolis, if I knew it exactly and I multiplied it by some number of 13-year-olds, I would have my best guess at how many of them should have cancer. If I knew the actual rate parameter. So that's what this is saying, that the rate times the time would be the mean number of counts. And there's this thing from the Poisson distribution that its variance, by the way, is also equal to the mean parameter. So the mean and the variance of the Poisson distribution are the same. Okay, that's different than the normal distribution, right, where there's this thing called the standard deviation, right, and the square of that is the variance, and that's a different beast than the mean parameter. The normal distribution has two pieces, the mean and the variance. In Poisson, they're equal. It's the same parameter. It varies as much as its mean. That's one of the properties of the Poisson distribution. And so you can actually this is a variant of the same formula we showed earlier for just the Poisson distribution in general, and you can rewrite it more or less as saying, well, for each subgroup, its count is distributed around its own mean, is basically distributed on its own mean. You can in theory model it that, well, each subgroup can have its own mean, which we're not exactly going to do. But we're making this assumption that each group can behave along its own Poisson distribution, and we're going to model how each group behaves. And I'll explain this on the next slide in a little bit. The key piece here is that this is a big assumption that the mean is equal to the variance, and these counts are distributed as Poisson. And this is not going to always be true. And I'll show you how to evaluate whether this assumption is true. So just like we had the proportional hazards assumption that said that the ratio of hazards in the Cox model had to be constant, just like we had this thing that was the proportional odds assumption, we're going to have this thing which is the Poisson assumption, that the data actually behaves Poisson. And what we'll see is that that's not necessarily always true. We're often going to have this thing called overdispersion, where there's a long kind of tail where we see weird kind of outliers. And you can also get this other thing called zero inflation, which is sometimes the event never happens in some subgroups. It's really rare, and there's an excess of zeros. And we're not going to talk about in zero inflated models, but there's ways for this to be violated. So it's a very strict assumption. And one of the easiest ways to actually inspect it, to think about this, is if you look at your data and the variance is way more than the mean, that may actually suggest that your data is not distributed Poisson. So anyway, this is just the assumption that we're dealing with. And the way, this is a lot on one slide, I'm just going to kind of walk through it in an overview way, but this is the likelihood function for the Poisson distribution. And the take-home message is just like we briefly went through the likelihood distribution for logistic regression, and we showed that it was really that you're maximizing the product of all these binomial distributions. Here, the likelihood function is a product of lots of Poisson probabilities for each subgroup's counts. So imagine you have 16 subgroups in our skin cancer example. You had 16 counts and person times and all of that. What it's really doing under the hood is it's taking the product, this is lots of big products, of each group 16 times, it's fitting this equation as a string of 16 products, and it's plugging in for this mean parameter, it's plugging in e to the beta naught plus blah, 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 whatever is in our model. This is what we are going to specify in our model. Across, it's going to plug it in for each of these 16 pieces of data, these different lines of code, and it's going to solve for the betas. That's what SAS is doing. It's solving for the betas through this maximization process. This is exactly what happened under the hood for logistic, but it was binomial probability formulas. Now it's Poisson formulas. And why did we plug in this e to the beta stuff? Well, remember, the model stated that the log of the rate, was of linear, and so we're doing the exponentiation of that, and we're plugging it in for the mu. This mean parameter is what we're specifying with our beta terms in our model. Okay, so that's in general what's going on here, right? So the whole mean parameter, this expected value of the counts thing, is actually, we're going to represent it by all the pieces of our linear model. And then we're going to plug it in, and SAS is going to solve for these betas. Okay, so that's the overview. I'm not expecting you to like close your eyes and write this. This is just the in general idea of what we're doing. So really, under the hood, we are modeling all the things that go into mu. And it is exactly fitting Poisson, the product of Poisson distributions. When you say dist equals Poisson, link equals log, this is what it's going to do. And so it's going to solve this equation for the pieces for these betas that you've put in here. And it's going to try to maximize the likelihood, right? So it's going to be iteratively solving and plugging in different values of betas until this L is maximized. And then it's going to say that's the most probable value of these betas for your data. So that's, again, the take-home message is this is actually what it's doing. It is directly what you're plugging in on that model line is going into a bunch of Poisson equations. So I just want to just zoom out for a moment. We'll do a little historical piece here, but the point is going to be to show you that there's several other important ways that the Poisson model is used. That vary a little bit on the surveillance, skin cancer, breast cancer kind of uses here. So this is Poisson regression 1.0. So in 1889, Ladislav, I can't pronounce, from Poland, or from Prussia, I guess, Greater Poland. He applied the Poisson distribution to data. So before the Poisson distribution existed as a probabilistic distribution. It hadn't really been, it had existed for sampling and probability and talking about gambling and other uses of probability from the 19th century. It wasn't really being used for statistical applications per se. And the first appearance of its use for a statistical analysis was in the late 19th century to look at death of Prussian army officers through horse kicks, which is this is a very famous example. I actually went back to the original paper and had fun with my amateur German trying to make it through. It's a really bizarre manuscript. And so, but here's an interesting data table. So this is Army officer. This is a data table of Army officer corps, and this is years. So this is a couple centuries ago. So this is 1875. This is the different 70s. This is 1875, 1876. And so forth. And these are counts of the number of deaths from horse kicks in these Prussian army corps. So apparently this is this is a problem of note when you don't have mechanized military and angry horses, or people that walk behind horses and shoot their guns or whatever they're doing. So you have these. So this is data, and the task was to actually analyze make determinations, I guess, around the effects of being in different groups, or certain groups more likely to be affected by fatal horse kicks or whatnot. And so the reason for bringing this up here is that this is a different application of the Poisson distribution that you do see a bit in the literature. And what it's doing is, notice this is still kind of group level data, right? This is Army Corps, Regiment 1 in 1878 has 2 deaths from a horse kick. There's no denominator to this. So the first application of Poisson kind of analysis has no person time per se. They didn't adjust for the number of people actually in the army divisions. They're kind of just assumed to have the same denominator. There's, 10,000 people in each regiment or whatever it is. And then here, this is actually just a cumulative probability distribution of the number seeing 0 kicks, number seeing 91, so the number seeing 0 kicks, 1, 2, 3, 4, and this is a summary table showing, and he goes to show how it's Poisson distributed. But the key here is just the counts get modeled. And so what you see sometimes for Poisson regression is the offset, you need to have it when there is actual differential person time. It's one group is observed for twice as long as another group. You need to put this offset in to take that into account. Otherwise, you're going to get the wrong answer because they've been observed for different amounts of time. But what you also do see is that people will model just counts using the Poisson distribution. Pure counts for people or things that have been observed for the same amount of time. So imagine the time is kind of, I'm trying to think of a good example. Let's say you're counting, you're looking at, let's say cancers again, and you're counting metastases on X-rays or something. Let's say you have a fixed field, and you're counting, or you're counting just some error or some issues, or metastases, I don't know, lesions, cells, whatever it is, you're counting it in some fixed thing, and you just want to model the count. You can also use Poisson distribution to model a pure count, and you don't have to specify the offset when that happens. Because it's the same, it's a constant. It's the same value for every observation, and basically everything cancels out, and you don't need to specify it at all. So all that's to say is that often when you encounter Poisson regression, you may see it and you're like, wait a minute, there's no rate. What's going on? It just looks like it's a bunch of counts. And that's okay. So this is another application, another way to use Poisson regression. And the basic idea is that the person time is assumed constant everywhere. And when that happens, you're okay. So that's all I'm trying to say. And also, I just think it's kind of fun to bring this up because it's just kind of funny. I think it's kind of funny. It wasn't funny for these folks, but it was very not funny. But the Prussian army found lots of other ways to die too. So so this is probably one of the rarer ways to have gone in the Prussian army. This guy also, I just love this. This guy's examples are horrible. So this is, suicides of kids, right? So this is suicides of children in Prussia. He modeled female suicides and deadly accidents. So this guy only was into unfortunate ends of people. But it's a very public health application of the Poisson distribution. He could have modeled economic activity. He modeled suicides and horse kicks. And he gave us the fundamentals of Poisson regression. Now, obviously, at this time, actually, linear regression hadn't even been formalized. So this is really, he was modeling using non-regression kind of approaches with the Poisson distribution. The linear model wasn't really well formulated for another 40 or 50 years. But anyway, I just think this is kind of interesting. So another example that's also illustrating this point and a different way of using the Poisson, thinking about Poisson regression is this example. And the moral of the story is that this is going to be an example that has, rather than group level count data like regimens with the counts of horse kicks or deaths from horse kicks, this is going to be about individual level count data. Similar to one of the other examples I just said out loud. So imagine a study where there's 80 people, and they've each been given 8 treatments. They're randomized to one of 8 treatments. So 10 people get 8 treatments, 80 people. And there's different combinations of drugs. This has gone over in the chapter in the textbook a little bit, so I'm just throwing this up here as another example. So you have 8 people. You have 10 people given 8 treatments, and they each give a bunch of cells that are. And the idea is you're looking at chromosomal damage in the cells. Hopefully, the cells were given the treatment, not the people. You're not trying to give people chromosomal damage. Hopefully, so hopefully you took the cells first and then you treated them, not the other way around. Not specified in the book. And so you have 100 cells from these people, and you expose them to one of 8 different exposures. And now in each cell, right, there's chromosomes, and you're looking for chromosomal breaks. So imagine in 46, 23 times 2 chromosomes, you have 46 chromosomes hanging around. You're looking at how many of the 46 are broken in this example. So the basic idea is that there's this sampling universe. There's up to 4,600, if you follow this through, there's 4,600 chromosomes that could be broken in a person because you took 100 cells from them. And you're going to count, the objective of this experiment was to count the number of chromosomes that were broken per person to understand whether one drug combination led to more chromosomal breaks than another. So why am I saying all this? This is a situation where it's count data. It's true, it's count data. It's got a really big upper theoretical limit. Hopefully that it's not going to get anywhere near 4,600. It's going to be like 27 and so forth. And it's the same offset for everyone, right? So everyone contributes the same number of chromosomes potentially to this. And so this is another Poisson. It's clearly going to be a Poisson regression kind of situation. It's a counts kind of thing. And you're measuring kind of the breakage rate in some sense, but it's breaks per person or breaks per cell or whatever it is. It's still rates and counts thing, but the person time is the same. And in this case, you can actually ignore it. You don't need to model or specify the offset in any way, and you can just measure the counts. So there's this caveat, in these kind of situations, you don't need to specify the offset. So here's kind of, here's just kind of a data layout for this. I don't think this is just a way to represent all the information here. And the point is, here's 8 treatment groups, 10 people, and these cells are showing 1 to 10 counts for the 10 people that got no treatment, up to this treatment combination. And the whole point here is that the offset for every single person is, let's say, if you did it as cells, it's 100 cells, or it's 4,600 chromosomes. Every single person has the same offset, and therefore you can ignore the offset. So that's all I'm saying, is that when you have this kind of business where everyone's observed for the same amount, it doesn't matter, and you just, in the analysis, you ignore it, and you can model it, and you can reconfigure it to talk about the per person, per 100 cells, per 4,600 chromosomes, It doesn't matter, everyone's the same in your analysis. So does this kind of situation, so this is a different situation than when you have groups observed for different amounts of time. This is different than we have this many people in this age group in Minneapolis, and the amount of observation time is also a determinant of how big the count is, right? If you observe more people, you might see more counts, and so you got to deal with that. But here it's standardized. Everyone's observed the same amount. So it's a different kind of situation, but it's still Poisson. On board? Maybe? Is there anything that, do people see how this is a different situation? Anything to clarify? We can make that, I know it's a very one-way orientation here, but you can yell things out or raise your hand to have let more order to it. Okay. Office hours, email, we're here for you. So this is a different orientation, still Poisson regression. That's all I'm trying to say. And here's actually a way to compare it, just to make the point more, to drive it home more. These are three very, very different things that can all be modeled with Poisson regression. Cases per person years, deaths per Army Corps, breaks per cells, right? They're analyzing drastically different things, right? Persons, city age groups, military units, right? This is the unit of the analysis is drastically different, and also the unit of the observations is different, right? The people that live in those subgroups is the actual smallest thing that's being measured. Soldiers, cells, or chromosomes in cells, or whatever it is. The counts behave differently, right? 0 to 1 for each person, 0 to 1 for soldiers, 1 to 46 per cell. You can formulate these things. These are three very different formulations, and they can all be done with Poisson regression. So that's all. That's all what this is trying to say. So that's just kind of our interlude to think about all the different data pieces here. So now we're going to jump a little bit back into we're going to jump very much back into the skin cancer example to talk about, okay, so we just saw at the end of the last presentation how to we fit a model where we controlled for age as a confounder. We looked at the adjusted rate ratio for city. It was 2.2. But what if you want to look at interaction? Right, remember we saw that there was some variability in the potentially in the rate ratio, right, across age groups. And what if we wanted to deal with that? So, okay, so here's a model this is an EVW model that thinks about the city by age interactions, or effect modification, right? Alpha plus beta times exposure, where exposure is city. Here is the 7 V terms for the age groups, right? We had 8 age groups, 7 dummy variables. And here are a bunch of EW terms that consider the city by age effect modification, right? And so we may want to understand whether there's any effect modification by city, so we might want to do a chunk test of this. And we may also just want to be able to know how to estimate the rate ratios for given city by age groups. So just like earlier when we did logistic and Cox model EVW stuff with effect modification, the pattern was that the V terms go away, and what you're left is an expression for the rate ratio that's e to the beta plus the sum of the gammas times deltas times W, right? So here, this is weird. I don't know why it says delta. It's actually written out. It's supposed to say delta as the character. But this business of the rate ratio now involves the EW terms over here. It's that same idea of where the V's go away because we're comparing the same in the numerator versus the denominator. The V's cancel out. So I spared the algebra here because it's exactly the same formula from the other regression models. And this becomes the rate ratio for city. Now it has to be it always has to account for which age group you're in. Oh, you're in this age group in Minneapolis. That means this is your rate ratio, and so forth. So now it has to involve the age groups as well. So some interesting things to note here. If you look at how many things are in the model, we have an intercept, we have an exposure. So an exposure term, beta times exposure, that's 2. 7 dummy variables for the age group. That's 9 total. 9 total things in the model, and then we have another 7 here for the product terms, right? So that's 16 pieces to estimate in the model. And how many rows of data are there? 16. 16. Right? There's 16 terms in the model. I kind of sound like a duck, I know. So that's going to be an issue. So we'll deal with that, right? So right, we fit a model that is both fully parameterized. Remember, the full parameterized model is a model that has all possible terms and all of their products in it, right? We only have age and city, and now we have city by age. So that's it. That's as many things as we could put in the model, given that these are the variables. So it's a fully parameterized model. But by the way, it's also saturated, right? And the difference between saturated and fully parameterized is all combinations of covariates that are in the model, and saturated is you have as many terms in the model as observations in the data. And this model is both fully parameterized because it has all the combinations, and it's saturated because it's 16 and 16. So we're going to have to think about that, because this should make you concerned. And it's actually not so grim in the Poisson model. In other models, fitting a saturated model leaves you unable to do very much, but here we'll actually be able to do a few things that are interesting with the saturated model. So let's assume that we can test for interaction in this model. The first question that you might want to do if you're doing our backwards elimination modeling strategy kind of stuff is you're going to want to first look at whether there's any significant interaction at all, or effect modification, the city by age piece here. And so you may want to do a hypothesis test of whether the 7 delta terms are collectively equal to 0, the chunk test. Right? That's going to be the first thing that you're going to want to do. And you're going to want to do it with a likelihood ratio test. Right? And this is this should be old hat by now. Right? The formula for the likelihood ratio test here is the -2 log likelihood of the reduced minus the -2 log likelihood of the full model. Right? And whereas the full model is this puppy here, it has everything, and it has the EW terms, and then you're going to have a reduced model that is going to drop the 7 effect modifier terms. And this is a model that it's a chi-square. It's a test statistic that is a chi-square distribution with 7 degrees of freedom given the null hypothesis. Okay, so this was true in logistic regression. It's true in Poisson regression. This is the same kind of setup that you'd want to do, but you're going to do it a little differently in GENMOD. So this is our test. But the thing is that we're not actually able to get the -2 log likelihood out of GENMOD. It's going to give us instead the deviance statistic. It's not going to give us the -2 log likelihood. But we're going to remember, as this slide will help us, that the deviance is a slightly different statistic, but it can be used in order to conduct a likelihood ratio test. And we talked about this with goodness of fit. In the goodness of fit lecture, we talked about using the deviance to describe the deviance from a saturated model and all of that fun. And one of the things that we said was that there's this tie-in between the deviance and the likelihood ratio statistic. And the basic idea here is that the deviance basically is a comparison. It's a statistic that compares. It represents the -2 log likelihood of a reduced model versus a maximum model. Whereas in GENMOD, it's the saturated model. So it's basically going to measure how different any given model is from the saturated model. So the saturated model in our skin cancer example is a model that has 16 terms in it. And it's a statistic that basically is the -2 times the log likelihood of your model over the saturated model. And algebraically, if you have 2 different models, imagine you have model A and you have model reduced and model full, and neither of them is saturated. The saturated model has 20 more terms. You have way more data than 16 observations, and you have a reduced and a full model. It turns out that the difference between the reduced and the full is this. Here it is right here, the reduced minus the full of the deviances. So you can write it as -2 times, you can undo this fraction here, Negative 2 times the estimated likelihood of the reduced minus this same piece of the saturated model minus that of the full model minus that of the saturated model. There's 4 terms to this expression. It's just written on 2 lines. These maxes cancel out. The saturated model stuff cancels out. And what you're left with is negative 2 times the likelihood of the reduced minus that of the full. So basically, when you're comparing 2 models and they involve the same saturated model that they're comparing against, the saturated pieces cancel out and you're left with this expression, which is exactly the likelihood ratio test. So all this is to say is that if someone gives you deviances for 2 different models and you take the difference of the deviances, you're actually left with the likelihood ratio statistic, even though these are not likelihood values themselves. It's the negative 2 log likelihood of a fraction of likelihoods. Okay, so all it's to say, these pieces are going to cancel out magically when you take the difference. And so, but the models have to be nested. They have to be subsets of one another in order for this to work. So one has to be reduced relative to the other. Okay, so GENMOD's only going to give us the deviances. It's kind of the problem. So, So in the Poisson model, I just basically said this, that the L max is going to be the deviance, it's going to represent the likelihood of the saturated model. This is going to vary from model to model. With the saturated model, this likelihood is going to be some weird quantity. It's going to between 0 and 1, actually, but it's different quantities. And we don't know what it is. It's the likelihood of the saturated model. And that is what the Poisson regression in GENMOD is using in the denominator, this likelihood of the saturated model. Okay, if you fit a saturated model, like, for example, our interaction model that had city by age interaction, remember we said it was saturated, it had 16 things in it, 16 observations. Oh no, it's saturated. In that case, the numerator piece, which is the likelihood for our model that we care about, is also is the same. It's the same. It's the same as the denominator. And I earlier said that the likelihood is always between 0 and 1. For the saturated model, it's always 1. So the numerator piece is the same as the denominator. If we fit a saturated model, it's going to be saturated model over saturated model. And you're going to get that the deviance is the negative 2 the log of 1 over 1, and that's just 0. Right? Because the log of 1 is 0. So this is negative 2 times the log of 1, which is negative 2 times 0. So the basic idea here is that if you fit a saturated model, you're going to get that its deviance is 0. It deviates from the saturated model by 0, which makes sense. It doesn't deviate from itself at all. It is itself. So just keep that in mind because we're going to use that in a moment. And remember, we used this property, this kind of idea and this thinking in logistic regression for not hypothesis testing so much as goodness of fit testing, because the idea was the smaller you deviated, the less you deviated from the saturated model, your model had a good fit, right? That was this idea like, well, the saturated model is a terrible thing because it fits as many parameters as data points. We don't want to use it. But if we can get something that's close to it, we have a good fit. That was the idea of the deviance tests. So now we're going to use this principle to conduct likelihood ratio tests. And so here, here's the model, the code from the skin cancer example, and now we're going to consider the effect modification of city by age group. Here we go. Look at that, 16 rows of parameter estimates from the intercept down through city by age group, well, 7. So notice here's these worthless rows with the referent group put in that we don't need. So here is what we get from including the effect modifier term. And notice the deviance is 0. That's because this is the saturated model. It is the same thing over the same thing. It does not deviate from itself at all. Okay, so this is not very informative for anything at the moment because the deviance is 0. But we want to conduct a hypothesis test of whether there's any significant effect modification. So what's the other model that we would compare this to? If we want to test whether there's any effect modification at all, what would we do to this model? Drop this. We're going to drop this. And that's going to have a non-zero value of the deviance. So now we're going to refit the model, and we're going to drop the interaction terms. And now we just have city, age group, no product terms. And now SAS says, here is your deviance statistic. It's 8.3. Okay, so this 8.3 or 8.2585 is something that we're going to use to actually conduct our likelihood ratio test of any significant interaction in the model. Okay, so we want to test these terms, these EW terms. We're saying, oh, the delta is all equal to 0. And we're going to do our likelihood ratio test by saying, okay, -2 log likelihood, this is the old way, but we said that we actually have to use the deviance. The difference of the deviances is equal to this entire expression. And so the reduced model had a deviance of 8.26, and the deviance of the full model in this case just happened to be 0 because it was the saturated model, 8.26. This thing on a chi-square degree of freedom 7 distribution yields a p-value of only 0.31. So you would say that we failed to reject the null hypothesis. And so in this case, you would say, based on this, that if you're just going by this alone, this chunk test, you'd say there's no interaction. Because there's not enough, that dropping them had a minimal effect on the deviance, right? You basically had, if you're thinking in your goodness of fit hat with how we talked about the deviance, dropping these terms you had just as good of a fit in your model. It didn't really matter. You fit almost the same as the saturated model. That's the deviance goodness of fit way of talking about it. Or you can say there was not a significant change in the likelihood, right? Which is the hypothesis testing from logistic regression way of talking about it. You'd say, well, the likelihood did not meaningfully change when I dropped these terms from the model. So we use the deviance statistic, which used to be our friend for goodness of fit. We're now going to use it for hypothesis testing here. And so you say, okay, great, not statistically significant interaction. Maybe I will, drop these, or maybe I will do. Now that's kind of all you got to do. There's no backwards elimination of effect modifiers to be done because there's only one effect modifier, right? There's 7 levels, 7 dummy variables, but it's all age. You're not going to break up age in some way. You're not going to say, I'm going to drop these age groups and keep the other ones. It's not going to work. So this is a chunk test of sorts because it involves 7 terms, but conceptually there was only one effect modifier, which was age. And so you'd stop here and you'd say, okay, there's no statistically significant effect modification. Let's go home. This actually just kind of summarizes what we more or less just said, which is that this is also, in a sense, a goodness of fit test, right? We just conducted a comparison between a model that had interaction and no interaction, and we said that was a test of the interaction, of the effect modification of city by age. But in this case, because we were comparing to the saturated model, because it happened to be that there were 16 terms, we also just did a deviance test for the goodness of fit of this model, of whether this model fit the data well. So you would use the same, you actually in this case could have used this deviance equals 8.26 observation, and you could do a chi-square 7 degrees of freedom test on this and say, get the same p-value because it's the same information. This was 8.26 minus 0 previously. This now also, it was a goodness of fit test of whether your model fit the data well against a saturated model. So this was a coincidence that the comparison, the full model happened to also be a saturated model, but you can imagine that's not going to always happen. You're going to have more data, more terms in your model, more complex things than 16 rows of data with 2 variables. So in general, you can use the single deviance statistic out of your model, whichever model it is. You can always use it to conduct a goodness of fit test for Poisson regression. Right? There's no minus other stuff to be had to this. This always reflects on its own, the deviance statistic always on its own is comparing your Poisson model to the saturated model. And so here you would say, okay, this is not significantly different from the saturated model. It also means that our Poisson model has good fit in some sense. The data is described well by the Poisson model. So this was just a convenient intersection. It's not going to always be that your interaction test is the same thing as the goodness of fit test, right? So imagine if you had a slightly different situation. You had 2 observations on every age group in every city, right? You had 2 eras or 2 sets, you had 2 different time points. So you had the 20-year-olds in Dallas and you observed them twice. So every cell has 2 observations and not 1. There's 32 records of data now, because you have twice as much data, right? 32 records. Now, this model, the interaction model, is still 16 terms. The data set has 32 people, 32 rows, still 16 things in it, still 16 pieces. Well, now, the deviance of the full model is not going to be 0 anymore. It's going to be something else, because this 16-term model is not the saturated model. Okay, now, right, does that make sense? It's different. There's twice as much data, 16 terms in the model. And so this interaction test is going to be different. This is going to be not 0, and it's going to be just a likelihood ratio test that you made from comparing 2 deviances. And that result of the interaction test is going to be different than the result of the goodness of fit test. Because the saturated model has 32 pieces in it, not 16 anymore. So these pieces, these 2 concepts aligned here, but they're not going to do that again in your life, or for a while. That this was just a convenient thing because there was 16 terms and 16 rows of data. So, okay, so imagine now you're listening to us as you always do in life, and you've now you've ruled out effect modification. You're going to go through your flow chart, and you're going to now assess confounding. You're going to assess confounding, and the only potential confounder right now is age, and we're going to now want to evaluate the confounding of the skin cancer city association by age, right? And that's so we have a single v variable, and we're just going to evaluate what happens when we drop it. It's pretty simple. There's no all subsets to be considered. There's only one subset, the one that doesn't have age. And this is what that looks like, right? This is the gold standard model. This is the no interaction model that has exposure and the V for the V's for age. And then you're going to look at a model that drops age, and you're going to look at e to the beta hat because that's the rate ratio. And you're going to compare whether there's a change in the rate ratio with and without age in the model. So again, same business as the other modeling forms, the logistic and Cox model forms. Same idea, compare e to the beta in the full and reduced models here, the gold standard and the age, the model without age in it. So this is what that would look like. You have to run 2 models, 2 estimate statements, right? Because we're not going to get e to the beta in any convenient way out of GENMOD. You have to explicitly ask it for it. So you run the model twice, 2 estimate statements, and this is what you get: 2.2, 2.1, and you're probably going to say, no confounding by age. In this case, is probably what you'll say, right? This is pretty close. But you can say 10% of this is only 0.2 something, right? 10% of 2.2 is 0.22. So this is still within 10% of the gold standard fully adjusted estimate. This is the fully adjusted piece, and this is minus age. So you'd actually say that there was probably no confounding by age either. So this is maybe an unconfounded. This is no confounding concern, except look at this. This is the but. There's a but. The model on the bottom. This is the one that the model with only exposure. It's a non-confounded model, right? In some sense. So it's the e to the beta is roughly the same answer. And you might say, okay, if this is all I cared about, I could report the bottom result and feel good about it and call it a day. But the model actually stinks. Because look at its deviance statistic. So 2569, 25, 2,500 is the value of its deviance statistic. And this is, remember, this represents the departure of the likelihood from the saturated model. And this little piece here is the ratio of the value over the degree of freedom, as it says. If you conducted a 14 degree of freedom chi-square test on this value, you would get a highly, 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 highly significant p-value, which means that you would reject the null hypothesis of good fit. Okay? So this is different than the likelihood ratio test using deviances. This is the goodness of fit test business that with the Poisson model. You would say this is highly significant. This has really bad fit. Okay, and this is not a good model. This one actually does have a good fit. I don't know how, do we have the, I think it's on a previous slide, I hope, somewhere, the deviance statistic. Yes, it is. It's 8, right? So this is 8, the deviance statistic of 8 versus 2,500, okay? This model does not describe the data well. Even though there's no bias in the rate ratio, it actually does not predict what actually is going on in the data worth much. And we can talk about why that is in a moment. I think if you may have a guess. Notice that SAS does not natively give you that p-value. So if you actually wanted to do a statistical test of with a chi-square 14 distribution and this value, you have to do it yourself. Using a data step, or you can use a table in a book if you have any books. You can do that, or just use SAS. But it gives you this thing, which is the value over the degrees of freedom. And basically, you can more or less ballpark the hypothesis test using this. So if the model has good fit, if there's, if the null hypothesis of good fit more or less holds, this ratio is pretty close to 1. Okay, so if it's 1, 1.5, and so forth, then you're pretty okay, probably on your hypothesis test. If it's 183, it means you will totally reject your hypothesis test. Okay, compare that to here. See, 8.3. This is the model that has city and age, no interaction, but city and age. 7 degrees of freedom. 7 degrees of freedom, 8.3. The ratio is this over this. The 8.3 over 7 is 1.18. This is pretty close to 1. And lo and behold, the chi-square test does not reject the null hypothesis. Okay? So when you see values of this fraction, value over degrees of freedom, it should be in the 1, maybe 2, or whatever, that kind of zone. If it's 183, you're going to find that the model has poor fit. And what this tells you is either your covariates stink, you're not modeling well, you're not describing, what's in your model is not describing the data well, or it means that the Poisson distribution doesn't describe your data well. Something's not working here. Either the Poisson does not describe the outcome well, or your covariates are not useful in describing the data. And why is that? So why would this model have poor fit? Why is this model poor fit? I'm going to give you let's jump back in time. Wait a minute. Do I have the data in here? We don't have the data here. You can call out while I'm scrambling for data. Maybe, not the people are still in there because of the offsets. Every row of data has offsets. That's a good one. So the goodness of fit is about describing the outcome well. How well does the model predict the outcome for a given row? And look, what's a really big determinant of the outcome? Age. Irrespective of the city stuff. City, makes a twofold difference in predicting the age. more or less, right? If you know the city, that gives you an advantage. More or less, Dallas rates are higher than Minneapolis. It's a twofold burden or whatever. But by far, the biggest determinant of the rate is actually the age. So in this model, this much, much stronger predictor is age, irrespective of the city. If I can know one thing about you to predict whether you're going to get skin cancer, is it going to be your age or whether you live in Minneapolis or Dallas? Turns out I'd rather know your age than what city you live in. The city piece only modifies my knowledge a little bit. I'll be like, oh, you live in Dallas. Okay, so your rate's about twofold that of Minneapolis. Oh, you're 85. Huh. You have 100-fold the rate over someone who's 20. So the exclusion of age actually yields a junkier model in some sense. It didn't bias what we got for the rate ratio. It still was 2. So the model achieved that kind of understanding of what the relative risk was between the two cities. But by leaving out a really important determinant of the outcome, we just have a bad model. So again, this is kind of just one of these dark art things, like how do you know how to build the right model? So you have to monitor you should really monitor this deviance and the goodness of fit alongside the risk ratio and the bias, kind of the ideologic stuff that we push about getting an unbiased estimate. Because you can get an unbiased estimate, but still have just reporting a bad model that's not useful in life. Because really you ignored the biggest determinant by far, which was the age. But luckily, if you monitor the deviance statistic, it's going to say, hey, this model actually is not good. Even though this was correctly estimated, your model cannot predict your data at all because it's really off from a saturated model. So again, there's no, if you want to make a flow chart for all this, you almost might say that maybe you evaluate this at the end. You might say like, I do this model selection stuff, and then maybe somewhere near the end, I'm going to be monitoring the goodness of fit of both of the models. Right? And maybe as an extra consideration, you might say, yeah, this gets you the right answer, but I'd rather report this one because this model is more universally useful to people out there for predicting the outcome. If you put a table of model results, I'd rather show this one because it shows the age adjustment and it's a better model to show. So, but again, you have to kind of be thinking in two hats, like what's the unbiased estimator of the rate ratio hat? And then, is this a good model in general hat? I don't know, it's a weird hat. But two different modes for thinking of here. So I'm going to jump into just some variations on this model, and we'll finish next time what we don't do today. This is an excerpt. This is a figure in the textbook in the chapter that we have online. This is just a cool plot that shows more or less the log of age versus the rate of skin cancer. And it turns out more or less the rate goes up linearly with the log of the age. So remember we showed this huge increase, right? 20-year-olds or whatever. The young folks have a very low rate of cancer, and to 85 plus is a very, very high rate. That's more or less an exponential relationship. So the log of age more or less is linear with the rate. That's what this plot shows. The scale is kind of funny because there's this formula to it, but basically it's a log relationship or exponential on the on the normal scale. It goes up exponentially, but the log rate goes with the log time. So the log of the rate goes with the log of age, I meant to say. So the log of rate with log of age. So and notice it's kind of the same by city. So no interaction of this, but the log of the rate is linear with the log of the age. And so you can imagine a different model. Here's another model, you might just say, where you don't fit categorical age. You can fit a linear term for age, but it's the log of age here. Okay. This thing is kind of psychedelic. So I don't know. This is a new variable that's a continuous variable that was made in the following way. You take an age group and you assign the midpoint to it. Here's the midpoint. And then the log of this is more or less what's used in the model with some minus 15 over 35. You don't have to do this. This is just what's in the textbook. But the basic idea is previously we fit 7 dummy variables to represent this, but more or less this goes up with the log of the age tracks with the log of the rate. So why not fit a single term, log of age, into the model and take advantage of this relationship that we observed in the data? Why treat all of the categories as unordered? That's not really utilizing the richness of the data. It's really this kind of linear effect on the log scale. And that's what we're doing here. So you didn't have to do it this way. This is the formula that's in the book. You didn't have to choose the midpoint. You could have done something else. This is just one representation of the information. But here's what this thing might look like. Here's the midpoint, and then you take this transformation, this minus 15 over 35, then you take the log of it. You could have just taken the log of the midpoint. Again, this is really what's in the book. But the point is, here's a single term now representing age, and that's a different kind of model. And you could fit this model, and you get actually a pretty interesting and similar answer as you would get with the categorical model. Some things to observe. We'll go there in a moment. First of all, this model has pretty good fit. Look at that. The deviance has 13 degrees of freedom, and this is because it's 16 is the degrees of freedom in the saturated model minus intercept, city, and then one term for log of age, minus 3, so that's 13 degree of freedom deviance test. And the deviance over degree of freedom is 1.1. So this fits pretty well. Remember, the model that did not deal with age at all had that 2,500 deviance. It totally was not good at describing the data. This model, with the addition of a single term that was the log of age, actually does a really good job. That's kind of cool. The rate ratio you would get would be the same as the other one, e to the beta. And you get basically the same answer as the model with categorical age. So that's kind of cool. We achieved the same degree of understanding in terms of the rate ratio, in terms of how good the model fits, by fitting a single log continuous term instead of a categorical term. So that's just kind of neat. It's a neat thing. Again, how did anyone know to do this and find it this way? This is an interesting exploratory exercise. I think that when you're considering putting categorizations of continuous things in your model, you should explore on the log scale, and if it's Poisson, how that variable behaves. And if it behaves in, let's say, a linear fashion, you can include it as a linear term in your model. If you were doing a logistic regression, you can actually make logit plots that logitify things, and you can look at the distribution of the data on the logit scale, and you can come up with similar things. In this case, it was a Poisson model. A plot of the log rate versus the log age yielded information like, hey, this looks kind of linear. And you really get the same answer when you put in a continuous linear term for the log of age. So that's just kind of cool. And so, here I'm going to see, I want to get to this actually. So I'm going to go very quickly through this, and I want to show you this table, and then we're going to end, and then we'll back it up at the start of the next class. If you want to test for interaction, it's going to be the same idea as before. We're going to compare we're doing a -2 log likelihood test, but using the deviance statistics. And we're going to look at a model that this model versus the model without this term, the one that drops the log of age. And notice there's no saturated model now anymore. The full model is this thing that has three variables in it, not 16. And the reduced model is going to drop it. It's going to have 2 variables in it. So it's going to be this is a different test than the interaction test that we had before. So I just want to throw this up here. This is the what we call the Poisson ANOVA table. And it's a way to organize a lot of the information about different models and make comparisons and statistical tests between them. And so each of these are different models that you could have fit to these data. Okay, now we've talked about categorical age, and we've talked about continuous age on this log scale. And if you constructed a table like this, you can make all sorts of cool comparisons. Okay, so for example, wait a moment. Okay, so here's this column shows all the deviances lined up, and these are all the degrees of freedoms, and these are all the numbers of parameters that are in our models. And here's the deviance over degrees of freedom. So these are all the key pieces that we've talked about for understanding goodness of fit and hypothesis testing. And what's cool is you can make comparisons very quickly in this table. So here, we could do a test of interaction between for age and city, just by comparing these two rows. This is the model that's just age but with no interaction. This is the interaction model. And you would say, okay, the difference in the deviance is 8.3. The difference in the number of parameters is 7. So it's a 7-degree of freedom test. And you saw there was no significant interaction. That was p equals 0.31. You can compare, look at this comparison. This is the comparison of a model. I didn't show you this one yet. This is the model we just fit a few minutes ago. This is continuous age. This is continuous age by city interaction. So a different type of effect modification. This thing has 3 parameters. This thing has 4. So the chi-square test that tests for the difference of your deviances is going to be a 1-degree of freedom test. There's only one thing being dropped. We'll go over this more next time, but I just want to throw this out here. And then the difference in the deviances is about 4-ish, and this is a marginally significant interaction. Okay, so on a chi-square 1-degree of freedom. So you can use this test to organize, this table to organize your thoughts. One way you get no interaction, the other way you do get interaction. So you have to deal with that. So that's interesting. And what's also cool about organizing it this way is you can see which of these models are good and which of them stink, right? So intercept only, not good. City and intercept, not good. We saw this before. This was the one that ignored age. And once you account for age, you have pretty okay fitting models. Notice this model and this model. These are models that have age but no city, when you consider age in 2 different ways. And these don't have good fits either. So you needed both age and city actually to have good fit. Kind of cool. We'll talk more about this. Have a good weekend.